Hello everyone and welcome to the third in a series of videos where I'm going over the entire build process and designing process of my largest and most powerful model rocket I've ever built, Velox E. If you're new here, my name is George and I've been building this model rocket called Velox E over the past few months. It's the first model rocket I've ever made to use any sort of electronics to read flight data and control components on board. In the last two videos I discussed the overall design of the rocket and the programming, and in this video I'm going to be talking about the assembly. Firstly, let's start with the Nosecone. As explained in the previous videos, this rocket will be using a servo motor to deploy the parachute. But how exactly? The Nosecone can be split into four main parts: the shoulder, the door, the frame, and the tip. The servo will be mounted inside the shoulder, which is a cutout precisely sized to fit. The rotating arm will extend out from the shoulder and the airframe, pressing against the Nosecone door. The door itself is the part that will separate at apogee. It isn't actually fixed to the rest of the airframe, the only thing holding in place is the servo arm. At both the top and bottom of the door, there are small tabs that slot alongside the frame to prevent the door from sliding back and forth. Additionally, there's a small hook at the top that fits into the Nosecone tip to stop the door from tilting outwards into the airflow and keeping everything nice and flush. The tip is essentially a small cone with a hollowed out section to provide space for the door's hook to slide in and out. The tip is fixed to the frame, which is then glued onto the shoulder. The shoulder itself will be screwed into the rocket's airframe rather than glued, so it isn't a permanent fixture and I'll still be able to access the servo. This design allows for the entire Nosecone to be detached from the rocket, making it possible to access the airframe's interior, which is crucial because of all the internal wiring. I also glued a small hook to the shoulder. This is where the parachute will be attached. I then marked a small cutout in the airframe for the servo motor to freely rotate and sold it out. After a few tries, I got the deployment system working. Inside the Nosecone, attached to the frame, I added a few layers of flexible plastic that I cut out from an old folder and taped at both ends. This just adds a bit of extra push from the inside to help force the parachute and the door outward. I was thinking of using some sort of springs to help push the chute out, but that would have been too complicated and could introduce a possible way for the chute to snag on the spring. Next up is the fin can. As mentioned previously, the whole fin section is going to be printed as one unit, mainly for strength. Before I can print it out, however, we need to get rid of those oversized shitty fins on Falcon Bobby 2.0. I definitely overestimated how big they need to be. They came off pretty easily, unsurprisingly, and now I just need to get rid of the stupid amount of epoxy and wood glue still stuck to the airframe. I heard that epoxy can be removed using acetone, which is a main ingredient in some nail polishes, so I bought some. I began just by chipping off some of the excess epoxy with a hammer and a scraper before applying the nail polish onto some sandpaper. It didn't seem to do anything though, even after applying some nail polish directly onto the epoxy itself. Maybe I just needed to wait longer or use some sort of chemical, but in the end it just made the room smell funny. And I was worried that pouring a bunch of liquid onto the airframe would damage it, so I just continued chipping it off. I then hopped onto the 3D printer and printed a small section of the fin can with the same dimensions to act as a sort of fit test. When it finished though, I only realized how thin and flexible it was. It might not have been too bad to have a bit of flex in there, but it seemed a bit too weak, and also the inner diameter was too small to fit around the airframe, so I printed out a second slightly larger piece, and that was too big. So I printed a third slightly smaller piece, and it fit just perfectly. Using these dimensions, I edited the fin can design and sent it to the printer. The slicer estimated I would take around a day and 14 hours. I kind of prayed to myself that it wouldn't take this long, but alas, as the day spilled into the night, I knew it was probably right. That rhymed. I had to get up multiple times during the night to check on the printer and make sure that it was still working, because if the print fails for whatever reason, I think I mentioned this before, the printer doesn't automatically stop. You have to do it manually, and if you don't, it'll just keep wasting all that ink on the print that's not even working. 2 days later, it was finally done. I'm actually very happy with how the fin can turned out. I was honestly betting on it failing a couple times in between and just having to retry from the very beginning, and also probably just getting another company to print it for me and spending a bunch of money on that. So I'm very happy and surprised that it worked flawlessly the entire way through. And this is going to be by far stronger than those individual cardboard fins that genuinely would wiggle if you moved it with your hands. I slid the fin can up the airframe using some epoxy, and it looked great. I also cut out another opening just above the fins, which will allow me to access the electronics. The payload bay will be a 3D printed compartment that will be used to protect most of the electronics on board, apart from the batteries and the servo. I began by printing the lid. I intended this to be a sort of twistable cap that I could easily take on or off to access the electronics. This cap would also have 2 holes for the servo and power cables to go through. The lid and frame came out meh. It twisted about a quarter of the way before becoming stuck, and I could do a bunch of sanding or just print another one, but even the partial closure fitted pretty well, so I decided to just use it as it is. Next, I printed the rest of the payload frame. The reason there's 2 slits on either side is because the breadboard wouldn't actually fit inside if the entire cylinder was closed off. But it also gave me better access to the electronics from the outside. I glued all these components together and slid them down into the airframe just above the motors. I cut a small hole in the side of the airframe just below where the battery case is for the switch. This was actually really difficult, and while I was trying to fiddle about getting the switch in the right place, it like disconnected from the wires and I had to solder it back while it was still in the rocket, and it was really... I forgot to film it because I was kind of just like gave up at that point. Thankfully it worked, but unfortunately during the process the payload bay broke a bit and the top cap came off, and I wasn't bothered to glue that back either, but it should be fine. It's protecting the electronics pretty well anyway. But now, because of this, turning on the rocket is as simple as flipping a switch. Next up is the recovery system. The parachute is pretty much the same as the one I used on Falcon Bobby 2.0. It's made from umbrella fabric, about 95 centimeters in diameter, with the suspension line connections reinforced with duct tape. The only difference this time is that it has something called a spill hole, which is just a hole cut out from the center of the parachute to let some of the air pass through. This is actually a very common feature and helps stop the parachute from swinging back and forth during descent, which should help prevent the lines from tangling or getting damaged in any way. The hole is about 10% of the total area. We're aiming for a descent rate of about 6 meters per second, which is kinda on the fast end for descent rates, and the hole will increase that a bit, but I think the extra stability is worth it. Another difference this time is that we're not going to be using a shock cord. Normally, the shock cord absorbs the force from the ejection charge and connects the chute to the main airframe, but since we're not using an ejection charge, we don't need one. Whoops. Speaking of ejection charges, how are we going to prevent the 3 motors in this rocket from actually firing its charge? Well, we're going to be doing this thing called plugging the motor, which basically involves shoving a bunch of epoxy on top of the motor to prevent any charges from escaping. It's very technical. Now this can be pretty unpredictable in terms of whether or not it's going to work, so in the event that the charges still escape, most of the pressure should vent out the back of the motor case and not up through the airframe, damaging the electronics. Ironically, the charges escaping through the back of the rocket is what caused Falcon Bobby 2.0's failure, but this time it works in our favor. We also drilled 4 small holes in the sides of the fin can just above the top of the motors, erring on the side of caution. With all that said and done, that's basically most of the rocket assembled. I am planning to paint this, by the way, don't worry, I'm planning to paint it all black. I haven't done it yet at the time of this recording, so if I've done it before I finish editing, I might put some footage over this of me doing it. And I also intend to have a camera case pointed looking at the servo arm during flight, and I need to glue that onto the side of the rocket. I'll put more footage of me doing that if I've already done it, because I haven't done it yet. I'm rushing this right now because literally, as I'm recording this, in a week's time, I am planning to launch this thing, so yeah. By the time this video comes out, it might only be a day or 2 before it's scheduled to launch. So if you're new here or you don't know about that, make sure you keep posted on the community tab of this channel to have the latest launch updates. The first photos and videos will be up on Instagram, so if you're not following me there, make sure you do so. And if we do go ahead with this launch next week and it doesn't get pushed back, a full launch analysis video will be coming out a few days after the launch. But yeah, I am very, very excited for this launch. I hope you guys are too. I've been working on this rocket since really the beginning of this year, essentially, and it's the most advanced rocket, quote-unquote advanced, that I've ever made. So yeah, I'm quite nervous, even though we're a week away from the launch. I have no idea if this is going to work. Obviously, the main area of concern for this is whether or not the parachute is going to come out. And I'm not really worried about the parachute not coming out. I'm more worried about it coming out too late or too early, mostly too early, for a number of reasons to do with the programming and everything. I'm just not 100% confident, but there's such little ground testing you can do to prove this sort of stuff, and the best way to figure it out if it's going to work or not is to actually fly the thing. So with that said, I hope you guys enjoyed this video. Sorry if it's a bit shorter than usual. I mean, it felt shorter recording it, so I don't know if it's going to actually translate that into video. If you're new here, again, please make sure to subscribe, and if you liked this video specifically, then I mean, you know what to do. It will really mean a lot. Thank you so much for watching, and I will see you in the next video. Goodbye.